I first want to apologize that I changed the name of the topic. So first, the talk name was Image Segmentation using Fully Convolutional Neural Networks, but we advanced after the deadline of submission and extended our work, so just making sure that you know that. So, and first of all, I want to interact with the audience a little bit. Can people who know what is linear regression raise their hand? So okay, good enough. And logistic regression? And neural networks and convolutional neural networks? Okay, that's less. Okay, thank you. So based on that, I'll adjust my talk. Thank you. So let me start. So I did my work along with my co-author in Johns Hopkins University, so my PhD student there, and my co-author is also a postdoc student there. So we wrote a library for image segmentation and object detection. So let me start my talk by first introducing you to convolutional neural networks. I wanted to bring it in a little bit different light. So I think it's a lot of material online about convolutional neural networks, but I wanted to bring some of my ideas about how I look at them and how they were basically how people came up with them and based on what ideas. So I'll start with introduction of logistic regression, linear regression, and their limitation. Then I move forward to multi-layer perceptron. Then I introduce Laplacian and Gaussian pyramids briefly and talk about hierarchical features of convolutional neural networks and conclude with convolutional arithmetics. So the main idea that I will try to convey in following 10 slides is that first, machine learning world came up with multi-layer perceptron, and a lot of ideas from computer vision research, like Laplacian pyramid and Gaussian pyramids, were captured from computer vision, and combining multi-layer perceptrons and Laplacian pyramids ideas gave rise to convolutional neural networks, and I'll explain about that in the following slides. So let's go further. So let's look at logistic regression and linear regression at the same time. So you can see that we can take any image. In this case, we work with MNIST dataset. It's a dataset of handwritten digits. So you can see a letter 8 on the left, and then we just flatten the pixels and run it through logistic regression to make a prediction. So on bottom, you can see the softmax function that basically gives you predictions of which digit this image belongs to. So this is a very simple model, and it's linear. So one of the problems with this model is that it can't model the interactions between input variables. So for example, it was if you go to Wikipedia page, you can see an example that this model can't represent interactions between variables. And more specifically, if you do linear regression, it won't be able to represent XOR function. So this is one of the limitations of this approach. So if we go further, if we stack, so you can see here it's just one layer. If we stack these things on top of each other and add nonlinearities in between of this, we will come up with multi-layer perceptron. This model is nonlinear, and it can represent very complex functions. So if we solve our task using multi-layer perceptron, we will receive better accuracy on MNIST dataset. So on the right, you can see the nonlinearities that people use in between. So one of them is sigmoid function. You can think about it as a probability. So it just maps input, which can be any real number, to a number between 0 and 1. So, and more recently, people introduced rectified linear units. This model also adds nonlinearity to the model, but it preserves some linear features of linear model, and it helps to optimize the overall model a little bit easier. So, and let's look at some models from computer vision research. So one of the models that I want you to point out is Gaussian pyramid. So Gaussian pyramid, you can see it on the left. So it's a representation of image on a multiple scales. It's used in computer vision research to do tasks on multiple scales. So imagine you want to find all the faces on the image, and some faces are very close to the camera, some faces are really far. So to do that, you'll have to run your detection algorithm on multiple scales. So Gaussian pyramid basically gives you image on multiple scales, and you can run your algorithm on all of these images, which was subsampled. And if you look at the right picture, it's actually a convolutional neural network, and you can see the similarities. So it starts with convolutional that are being applied on the full resolution image. Then it gradually subsamples the image, and further going down, you can see that we basically get representations of the image on a higher level. And then basically, when we reach the bottom level, we get higher level features as faces or other things, and based on them we can make a prediction using the logistic regression on top of it. So basically what I want you to understand so far is that by combining those two models, multi-layer perceptron and convolutional neural networks. Not convolutional neural networks, but Gaussian pyramid and Laplacian pyramid here. We can see that it's kind of like combined those two worlds and came up with a very rich feature representations. At the same time, its multi-layer perceptron helps you to make a decision at the end. And also, you can see there is another model, it's called Laplacian pyramid, which is a little bit more closer to what convolutional neural networks learn. So Laplacian pyramid, it helps you to represent image on multiple scales, but also it grabs a certain frequency information from image. So if you look at the left picture, you can see the picture of Lena. And the first information bit, I don't know if you can see my marker. Can you see it? Yeah, so this one represents really high frequency information of the image. Then if you gradually go and go, we get low frequency information. So Laplacian pyramid helps you to spread your image into different bands, basically of different frequency, and then basically make a decision on top of that. If you look at the representation of image in convolutional neural network, so you can see we can get an input as a picture of a cat. And then here we can see the activations of first layer. So you can see it's like a higher frequency information. So some of them captured the gradient information. Some of them captured gradient in other directions. But if you go further here, I don't know if its contrast is good enough to see that, but some neurons here, they activated on the place where the cat's face, you can see it here, for example. Yeah, I guess this one. Some of them activated where a cat has legs, so you can see it here. So it's very interesting to see this analogy between Laplacian pyramid that was introduced already 30 years ago and convolutional neural networks. But the analogy is not enough, but it's good enough to get some grasp of how it works and basically structure your algorithm correspondingly. So also one of the main important features of convolutional neural networks is that they learn features hierarchically. So this network was trained on faces, and you can see that first layer weights, they represent some edges or blobs. Then we go further and we see ears, eyes, and then we go further and we can see more high-level structures like the whole parts of the face. So this is also important because by the end of we want to run our image through the network and get only high-level features based on which we want to make the final decision. So, and just a quick recap about convolutional neural network arithmetics. So you can see that convolutional neural networks, they basically use convolution. And one of the two main things in convolution is padding and stride. Padding is used to basically to adjust the output size. So if you can imagine, if you run convolution on top of the image, sometimes you get output of the different size, and basically padding and stride, they regulate that. And using those two, you can regulate subsampling that you do in your network. So on the right, you can see just a high-level picture of how the subsampling works when the features go through the network. So you can see on the top, we have like really high feature information, then we go lower and lower, and we get subsampled features. So let's go further to dense prediction tasks, a bit like the main topic of our talk today. So dense prediction tasks, we can structure them into multiple things. One of them is semantic segmentation. So you can see an input image on the left, and semantic segmentation, basically, you need to label every pixel in the image with corresponding class. So you can see horse and the person there. So what ideally we want as an output is this representation as labels. Also another task include like depth estimation from monocular images. So you can see the input is a table and chairs, and the output is a depth map. Sometimes we also want to do boundary or edge detection. So we get an input as an image and we get an output as edges. So all of these tasks are very important in computer vision, and sometimes they can be applied as a part of the higher level, some more smart algorithm. So let's look at the traditional image classification convolutional neural networks. So they get input image, and then they basically give you output of 1,000 dimensional vector, which gives you basically prediction of what it thinks in the image is. So majority of image is occupied by the cat, so it thinks it's a tabby cat. But so if you look even closer, network consists of convolutional layers and fully connected layers. And for example, for tasks as image segmentation, we have input images of different size. And we don't want that. We want it to be more flexible. So one of the problems that we face when we want to do this is fully connected layers, because fully connected layers, they have input feature maps of fixed size, and convolution can have input of any size. So we have to remove this frontier to be able to input any image size. So this is done by converting fully connected layers of network into convolutional ones. This way, we can input image of any size and get corresponding predictions. So here I visualize the feature maps. So you can see we input image of size h by w, and we get a feature map which is reduced by a factor of 32. This is just an outcome of the fact that we do subsampling in our network. So let's take any just a standard convolutional neural network like VGG16 and run it through the image of bus. And we can see that even without training specifically for segmentation, it was able to give us prediction map. So you can see in the center we have a prediction for the bus, but on other parts we have like some scattered around predictions. But it's very surprising because this network wasn't even trained to do segmentation. It was just trained to do classification. So one of the problems with this previous approach is you can see the prediction is subsampled. So it's subsampled by a factor of 32. We don't want that because we want to prediction for the whole image. So one of the ways to go around this is to add upsampling layer. Basically, it's just like bilinear upsampling, but it's differentiable, so we can plug it in our network and perform training. So this is what we do here. So if we just take the same network without training and put upsampling on top, we get the predictions which are the same size, and you can see they are more smooth. So now, to perform training, we only have to add ground truth on the right part. Ground truth is a ground truth which was annotated by professional annotators. And this way we can train our network to show what we actually want to do. So in this case, we give it an image on the left and the ground truth of segmentation on the right. We perform training, and then we see what happens. So just to give a better idea of what's happening inside. So we get an image on the left, we run it through the network, then it gets downsampled, then we upsampled once again, and get pixelized predictions. So in order to show network how accurate its prediction is, we plug cross-entropy loss at the end and sum all the values. To give you a hint, it's the same loss that is used in image classification. We just applied it to each pixel and summed it over. So let's run our network on just one image and see what it does. So in this case, we train it only on one image, not a huge data set. And here I will show you how it actually learns to see cats in this picture. And I will visualize the iterations gradually. So on the first iteration, it just gives a small prediction, which is not accurate at all. But then if you go further, it kind of starts to grasp what's there. And finally, we get some kind of good prediction. But the problem with that is that the prediction is coarse. This is the reason because we just upsampled the feature map that was subsampled by 32, and predictions are very coarse. So we can handle that by using skip connections. Basically, skip connection, as you remember previously, when I showed you visualization of activations of function on different layers, one of them are responsible for edges. So what exactly we want in this case is incorporate these edges and lower layer features into our inference, so the network can actually adjust its coarse predictions to edges and like very specific parts of the image, and finally come up with a really nice segmentation. So I will show you just the final result. We trained this network on the Pascal VOC. It's an image segmentation dataset with 21 classes, and it contains 1,000 images. And you can get predictions like of something similar to this. So if you compare it to previous result, this segmentation is very accurate and it looks nice. So I'll quickly go through like other improvements in the field. So I don't have enough time for this talk, but I left a lot of information in the comments to my presentations. So if you'll go through them and read all of my comments, I leave a lot of links so you can go further and dig like a lot of by yourself. So one of the recent improvements that were done in this field is dilated convolutions were introduced into field of image segmentation and other dense inference tasks. So also you can use condition random fields, which can be used to refine prediction. And one of the recent works, which was done just recently and will be presented on CVPR next week, is mask RCNN. The idea of mask RCNN is that they do detection first, and then they regress the mask for the detected object. So they kind of couple two tasks together, object detection and segmentation. So, and I'll also feature one of our works. We applied this work to segmentation of surgical tools. So we used dilated convolutions with one of the standard architectures which was introduced recently, ResNet 101. So, and you can see that results that were delivered by this model was really good. And one of the benefits of this model is that you can train end-to-end. In the previous model that we showed, you have to train in stages, and it's kind of cumbersome. So let's see some applications. So one of my co-authors allowed me to use his picture to make some fun of him. So, like, first of all, you can just do segmentation on any images, like selfies in this case. So you can crop them out and just use them as any messenger. Like, that's kind of fun. But also, like, let's go back to my friend. So this picture looks boring. Let's add it to some other background. So it's actually him on the back, like, I know, here. Then also, if any of you have iPhones and you're familiar with portrait mode, you can also do effects like portrait mode. So portrait mode is, for you who are not familiar with that, is that it takes object that is very close and focused on the image right now, and it blurs out all the background. So in this case, you can see on the left that's the original image, and on the right image, everything was blurred out except the object of interest. In our case, it's my friend. So let me briefly then conclude with my talk. Yeah, I provide all the links, and I think that the presentation and slide and code will be shared. And if you want to know more, I left a lot of additional information in addition to each slide. And I hope you like my talk. Thank you, everyone. And if anyone has questions, you can ask them now.
I have a question.
Okay.
Where do you see this work going in the future?
What?
Like, what are your next steps for this project?
Oh, I'm basically a PhD student, and we're applying it to medical segmentation images. So we try to couple the segmentation detection to better understand the surgery. So during surgery, it's very hard sometimes to see what's happening there. And one of the problems that we face is pose estimation of surgical tools. And we apply all these image processing methods to do it better. Something like this.
I'm curious, you have both implementations in PyTorch and TensorFlow. Which one do you recommend more?
Oh yeah, that's a good topic though. So first, I'll tell you my story. So first I implemented it in TensorFlow. I spent a lot of time on it because it doesn't have a lot of documentation. You just have to read a lot of source codes with examples. So I finally wrote it. The results were good, but one missing thing that was missing in TensorFlow is that it's not really flexible. So if you want to experiment a lot, which is very common for research, I would recommend PyTorch. But in case if you want to do or apply this in an industry, like some real-world scenarios, I would go with TensorFlow. But you can always convert weights from both of these frameworks. So I think the good idea is to deploy, when you want to actually deploy it, you'd better use TensorFlow. But for research purposes, I would find PyTorch better.
Mm-hmm. Thanks.
You're welcome.
So you mentioned medical applications. Have you given any thought to applying this to segmentation of micrographs for material science?
Oh, that's applicable to anything. The only thing, to any kind of problems. So the only thing that you have to provide this algorithm with is ground truth and images, and then it can learn everything. So like around 400 images should be enough, usually.
Thanks.
Are there any notable limitations in like the type of images it can and cannot segment? So like regarding sharpness or color space or stuff like that?
So sometimes you have to segment really, really fine objects. Like sometimes we had to segment let me give you a good example. So it was just a stick that was really thin. And sometimes you have seen that networks have problems with thin objects because they usually give coarse predictions. In that case, you probably have to use a little bit different architectures, but it usually depends just on your data set. Sometimes like some adjustments are required, but what the problem that I noticed is this small scale objects. Sometimes they have problems and you have to use different architectures.
So say for that, like in the images you've worked with, like medical images, pictures, you haven't noticed like any salient difference in what types of images it deals with better? Yeah,
the way we approach our problem is that we take network that was trained on huge ImageNet competition. It's like around 1 million natural images. So we notice that if we use these weights as initialization for our network, it adjusts really well. So all of the features that it learned from natural images adjust to medical application scenarios. So yeah, this is basically high-level idea.
Once you've trained it, how long does it take to segment an image?
Oh yeah, let me actually show you. If you can go. So if you follow the link for the library itself, we have timing for some of the networks. So the fastest I achieved, like just previous week, it was 28 milliseconds. So it's on a Titan X GPU card. Yeah, of course you will need GPU cards. I forgot to mention. It's very, very long to run on CPU.
Okay. Thanks. That's
Yeah,
helpful.
you're welcome. Yeah, I think nobody else have questions. Okay. Thank you, everyone, once again. Have a good day.